Yep, recording has started.
Thank you very much, Erwin, and welcome everybody to this session on Predictor LimA version 2023, where we'll be running through some of the selection of the highlights of the new version of the software suite. So my name is Douglas Manville, and I'm sales manager for Predictor LimA, and Erwin is the managing director of SoftNoise, and together we will be guiding you through this webinar. So the agenda we had thought of for today was, first of all, to remind you why we think Predictor LimA is such a good solution. For those of you who use it, I'm sure you know this. Maybe if you're new to Predictor LimA, it's good to hear this. We will then describe a little bit about the release of the new version, and the main part will focus on presenting with a few demonstrations of the enhancements, first in Predictor and then in LimA in the new version 2023. We will tell you how you can access the latest version and also the new license files that are required to use the full software, and guide you where you can get further information. We will hand out a recording. Sorry, we'll hand out the handouts of this this presentation to you after the meeting, and in addition, we will make the recording available. We plan for time for question and answers at the end of the session, both during the recording and also when the recording ends. And of course, we will conclude with the conclusions. So let's start off a little bit about Predictor LimA, which we believe is the market's most powerful and intuitive software for environmental noise calculation. It's a very efficient software, as it's a suite that bundles the intuitive predictor and the flexible LimA into one powerful, integrated, state-of-the-art package that we believe provides the best solution for every project. Together, the functionality of Predictor and the flexibility of LimA allow you to quickly and easily make calculation and analysis of environmental noise. Predictor in particular makes real-life modeling in accordance with standards very quickly and accurately, while LimA provides tools to do in-depth specialist work and also to fully integrate environmental noise calculations in other systems. So regarding the new version, this was released at the end of December last year and provides new and enhanced functionality and bug fixes. And new license files are required for use of the new version, and these can be downloaded from our website, softnoise.com. So first of all, I will guide you through the enhancements in Predictor. Well, not all the enhancements, just some selected ones. I'd like to tell you about the new options for railway calculation using the Knossos method, which resolves a vertical directivity issue that's created within the method, and also dealing with the aerodynamic noise. In addition, there are improvements with wind turbine functionality, which follow the Institute of Acoustics Good Practice Guide, and we will show you some of the, describe some of the improvements. There's a more flexible interface with GIS through some new import and export formats, and we'll show you this, in fact, demonstrated. In addition to that, when we're talking about import of data, then we now support EPSG code and Predictor, and this eases the integration of different sets of data with including the automatic conversion of coordinates, so you get the right data in the right place. It's easy now to lock and unlock models through the lock and unlock function, which we'll show on the quick link tabs. And then if you're working in New Zealand, and the CRTN New Zealand Road Surfaces database has been updated to match the latest official version. Sorry, I almost forgot to do that. And then we also piggyback off the LimA calculation speed enhancements which are available with new options there. So let's start off with railway in the new European Knossos method. First of all, if you look at the graph at the top right-hand corner, you'll see the directivity pattern of the rolling noise, which is a major component of a railway noise. And if you look at the elevation angle, you'll see that the directivity increases initially and then decreases quite sharply and quite dramatically at high vertical angles. This means that when you're making a calculation point almost directly above a railway centerline, you get overall levels that drop 10 to 12 decibels compared to adjacent positions just because of this directivity factor. And this vertical directivity equation was changed in the delegated directive. So to avoid non-intuitive levels along railway lines, we introduced something called SMIN, which has been around in LimA, and this is now implemented in Predictor. So on the right-hand side, you can see a graph of if we don't take account or if we do take account of the vertical directivity, the impact of this on noise graph. So this is just a graph of a noise grid above a railway line, and you can see that the noise levels are lower just above the railway line. Now that's fine for us, but it may look counterintuitive on a noise map to the general public. And here on this picture here, we can see this 3D directivity, what it means actually on a railway line. You can see there's an angular directivity on each side of the track, and then a sharp drop in emission above the track. If you use the SMIN, a minimum 3D distance, you set this, you can get graphs to look like this on the right-hand side. And normally when you make a full calculation, your SMIN is set to 0. And we now have the possibility to put this at 3.75 meters or 7.5 meters or any distance we wish. And if you put these values onto a grid of 4 or 5 meters above the railway, then you'll not see much difference on the what you usually expect to see on contours. And I'll show you this on the next slide here. So this is a slide where I have 3 identical models, but the calculations are made with 3 different settings. The one on the left is the true Knossos results, where you have an SMIN of 0. So all the grid points are calculated, and here you can see we have a traditional 3D BPW of distance line source, but in the middle you have this impact of the vertical directivity. Maybe you don't want to show this or see this. Thereby you can set it to 3.75. So all of these are with the 4 meter high grids. If we set the SMIN to 3.75, you can see a very nice, larger level of noise, as you would intuitively expect from a line source. It's not quite right, though, of course, because of the vertical directivity. If you set it to 7.5, you get this compromise where you still get high levels close to the source, which is intuitively correct, but you hide this dip that you can see here. It's not quite the same as here, but it's a compromise. So you can see here by setting SMIN somewhere between 3.75 and 7.5 for strategic noise maps, you can get data presentations that look intuitive to users or to the population. Another aspect of railway noise is a component of aerodynamic noise. And the European directive, which is the Knossos method, states that aerodynamic noise is only relevant above speeds above 200 kilometers an hour. And if train speeds in a network are above 200 kilometers an hour, but limited to 250 kilometers an hour, then in some cases it may not be necessary to include aerodynamic noise, depending on the vehicle design. And this has led to the fact that different countries have set different cutoff speeds on when to introduce the aerodynamic noise, and also on specific layouts. If you only have vehicles or trains traveling up to 250 kilometers an hour, then you may choose not to have the aerodynamic up to the speed. So, for example, Spain uses the setting of 250 kilometers an hour. So now you can set this. You have already been able to do this in LimA, but now this is available in Predictor. And you can see this in the calculation settings, which are shown over here on the right. Here, the lower limit is 200 kilometers an hour. I can set this to 250, and then the aerodynamic noise would only contribute above 250 kilometers an hour. Moving on to wind turbines. We've further improved the functionality for modeling wind turbines following the IOA Good Practice Guide, which deals with wind turbines. And there are two things that we've improved within the table of wind turbine results. First of all, we now support the V10 wind speeds. That's the velocity at 10 meters height. And you can see here, that's marked up here. The other thing that we have done is the support of groups of wind turbines. So this set of results is for the main group, where multiple groups of wind turbines are included. And if you look at the values here, when I change the group to only look at one group, you will see that the numbers change, just to prove that we're only looking at the results from this group of wind turbines compared to the main ones. In addition to that, you have a natural situation where wind turbines, for example, here at the top of a hill, and you have a valley situation on either side, for example, of the wind turbines. The Good Practice Guide says that you should add a correction of 3 dB when you have propagation across a concave ground profile. So this would be in this sort of example, we have a concave ground profile with hills here and hills here, and then a valley here. However, it also states that you should not apply that in the case of screening. And this would be the case when you have a village in here. So a village in here, you don't apply the correction. And this is now accounted for in the calculations in Predictor LimA. So you can see an illustration of screening, but this is not a true concave ground profile. This is more true up here where you have hills on the other side. In addition, for wind turbines, when you select a turbine from the wind turbine catalog and you add it onto a source in Predictor, then the name of the wind turbine from the catalog is added to the description, make it much more intuitive to see which source has been used. Moving on from wind turbines, let's now look at geographical data. So we now have some additional new formats of importing data: an Esri file geodatabase, a geopackage file, and a GML file. Now, geodatabase is, as its name suggests, a collection of files in an Esri format, and it's for storage and querying multiple files. A geopackage file is a SQLite-based compact format, which is open and standardized. And finally, a GML file is an open GIS geography markup language encoding standard, which is not limited to Esri, but is open. These file formats do not have the limitations that traditional shape files have. So shape files are great, but these formats are even better. So they don't have the limitations on the number of files that they can be included. They don't have the limitations on the character length of the descriptions, of the size of the file, or of the numbers of objects or types of objects within the file. And new import and export options for Esri file formats and the open file format are now available, as you can see over here on the import tab. And what's nice and what I'm going to demonstrate is the import is much smoother because you can support multiple item types. So let me move over to Predictor. And here you can see a model, and I'm going to show you first of all what I've always been done and been very happy to do, and that's importing a shape file. So I got to a set of data that I have, and say, okay, let me have the buildings, for example. I open the building file. I choose that layer, identify it as being a building, and make sure that my data matches, which of course in this example it does. And then I import the buildings. I would then go over to my roads and import my roads, doing the same thing, selecting that they're roads and doing that and making sure they're selected and there. That's nice and easy and nice and quick. But with the new formats, we can do something even better. I'm going to go and use an import, and this time from an Esri geodatabase. The geodatabase is a whole collection of files. So I got to that here, and I go to my geodatabase folder. So now I'm selecting a folder rather than an individual file. So I choose that, and now I can see the contents of this folder. And it's got multiple objects types in it. So I want to import the roads because there are lots of them, and I want to import them as road items. I've got calculation grids. So I also want to import them as calculation grids. And if I go here, I can also see I've got buildings in the database. I select the buildings. And when I do that, then all three object types are imported in one go. Very nice and smooth. While we're talking about importing data, then we should really talk about EPSG codes. And Predictor now supports EPSG codes in model information, which is an identifier for which local coordinate system you're using. In addition to this, this allows you to convert or enables Predictor to automatically convert objects with different EPSG codes, or from files that have a different EPSG code, sorry. And this makes it integrating different data sets much, much easier. If the file you want to import has an EPSG code and your models has an EPSG code as well, then the data is converted automatically and correctly, even if the EPSG codes are different. And if your model does not have an EPSG code, you're able to select this during the import. As you can see over here, this is the dialog box that comes up, and you enter the EPSG code down here. Once you have set the EPSG code of the model, it will correctly import the data sets with any EPSG code. And as you can see from this example here, which is from Amersfoort in the Netherlands, we have 3 sets of data just highlighted here, all covering the same geographical area, but with different EPSG codes. So you can import each set of this data and it'll be correctly converted into the reference projection that Predictor is using in the model. So different sets of data may have different EPSG codes. For example, older data sets or sets from different sources such as Google Earth or OpenStreetMaps or from local authorities. So an example is if you import height lines with an EPSG code of 32640, you can manually set the EPSG code of your model to this value. But then when you import, for example, OpenStreetMap data of that region, the data is automatically aligned, fitting the height lines, and that means without you having to do any manual work. EPSG is a public registry of coordinate formats used by most GIS, for example, QGIS. And if you want to find out what the code is, you can. We have put in 3 reference sites where you can search for the EPSG codes. And if you're interested in learning more about EPSG, then we found an interesting video by a Dutch professor in English that you can watch. It's quite enlightening. Let's now move on to one of the quick links. So we have added an option in the quick links on the right-hand side to lock and unlock a model. And you can see here on the quick links, we've got a model read-write option. So on this version here, I've got the model read-write deactivated, and the model is locked, indicated as here. If I push the slider, then I can activate the read-write mode, and the lock disappears, opening up the model. So this is a nice and quick and easy way for you to protect data, or for you to unprotect data, for example, to enable editing. So if, for example, you have had done a calculation in the Predictor LimA calculation cloud server, that will traditionally be delivered to you locked to protect the results from inadvertent use. You can very quickly unlock those and begin work on a copy of that model. Moving on to another enhancement then for road surfaces, we found that there was a small issue with road surfaces in the New Zealand version of CRTN, and we've updated the database now to match the latest official version, which is the Land Transport of New Zealand Research Report 326 from 2007, so that the database now correctly matches this. And I think that the issue we found was that the slurry seal was either incorrect or missing. And that's now fixed. That was Predictor. And now move on to LimA. So let's have a look at some of the selected enhancements that I'd like to talk about today. First of all, we've got better handling of national interpretations of the EU directive, for example, regarding exposure statistics. Now, this might be a little bit in niceties, but it's quite important to understand, and I'll work through that. In addition, there's easier management of different variations of the same project, workflow support and building reflection losses. We've done this for Germany, but in principle, it's open for other countries as well. And it's a way of enabling you to manage both types of calculations without changing the model. Calculation speed is also improved through a range of enhancements, and this is particularly important for larger models and for more complex methods such as the Knossos method. In addition, it's possible to look at a number of groups are influence on receiver points on facades, and that's using the Barrett Max Source function, and that gives you an easier model analysis and more insight. In addition, there's a very simple way of correctly modeling railway bridges in Knossos EU when you have to retain these bridges also for use in other areas. I'll go through all of these, but of course, in addition to that, there are diverse specific enhancements and bug fixes that may be important or useful for specific projects, and I won't go through those today. So let's have a look at interpretation of the Environmental Noise Directive. If you're outside Europe, you can be happily, don't have to worry about this, but perhaps this is interesting for you anyway, because of the impact it has. Now, the directive says that you have to classify and group your noise in 5 dB intervals, provide statistics in 5 dB intervals, 50 to 54, 55 to 59. Okay, but what do you do between 54 and 55? Well, the directive's not too clear about that. Therefore, a report was made and it's published by the European Environment Agency on guidelines for strategic noise mapping to deal with this. And it has some recommendations, not mandatory, but recommendations. And it recommends that all class boundaries are from that 5 dB step up to almost the next one. In other words, it's using truncation and not rounding. So 59.99 does not get rounded up to 60. It remains as 59. Now, this is consistent with noise contour lines that describe where the noise level exceeds 55 or 60 dB. And for dwellings and schools and hospitals and people in dwellings and exposed areas, the report recommends that you use the same 5 dB classes. And it means that you either have to make a query to find out these values, or pre-process the results and assign them to the correct 5 dB band. But the fact that this is a recommendation allows for different interpretations. And in fact, different countries have different interpretations of the directive on this point. So we have to deliver a solution for everybody, which means we have to deal with this. So, for example, if you round your results with a 0.1 dB resolution, then your 50 to 54 dB class is in fact somewhere showing results from between 49.9 dB and 54.9 dB. If you round your results to 0.5 dB, then your 50 to 54 class then represents 49.5 to 54.5 dB. And if you use the method up here, then 50 to 54 dB means you've somewhere between 50.0 to 54.99 on results based on truncation to 2 decimal places. That's just a European legislation. However, you also have typically national legislation for other uses, and this may also differ in interpretation. Traditionally, in Germany, for example, then 50 to 55 has been 49.5 to 55.5, which you're rounding the levels. So we got to deal with this, and it needs to be handled as a variable. So to know a little bit, you need to know that LimA uses 2 decimal places in the result file, and it then is rounded. So that's the basis. The area polygons are named as, for example, 50 to 54 dB, and the default class assignment works on rounded levels with 0.5 dB resolution. So in fact, your 50 to 54 dB class is somewhere between 49.5 and 54.5. However, the END with Knossos, the Environmental Noise Directive, requires truncation, and this is a new option that we've introduced in LimA 2023 that enables us based on the 0.1 dB resolution as recommended in the published recommendation. And to do this, you go to your general settings on Environmental Noise Directive, and you set the Knossos rounding value to 0. This impacts all the calculated contours and statistics and is documented in the object PR file with this text here. And this text is put into the graphics header line input to use. You need to update your object PA, then you just create a new project with this setting and then close it, and you're off and got running. So with LimA, if you want to have results rounded to 0.1 dB, you set this to 0.1. That will give you a 50 to 54 class, representing 49.9 to 54.9. If you use 0.5 dB on rounding, then the 50 to 54 will be 49.5 to 54.5. And if you use the EU default or the recommendation, you set that to 0, you truncate your results to 2 decimal places, and your 50 to 54 would represent 50 results between 50 and 54.99. So all of this affects the statistics on exposed areas that are done. So we in Europe make things make a little bit difficult at the moment because we also have national requirements as well as the ones we are doing for the strategic noise maps for European Union. And these national needs and definitions and settings sometimes differ from the EU requirements. And if you can do this in an efficient manner without having to duplicate your model, that's very useful. So for example, the German RLS 19 road regulation uses specific different reflection loss settings than the EU requires. And these dual requirements for Germany are now supported in LimA version 2023. In principle, they can be available for other countries. So if you need this in somewhere else, then we can support this in LimA, and you just contact us for that. It's maybe easier to understand this if I give a little bit more detail of what's done for the in German situation. So first of all, you just this is taken care of in the calculation. So simply, when you select an RLS 19 German road calculation with a model, then it will change the use of the attributes in accordance with the requirements of the German one. So you just set up a model that's used for Knossos and add on the attributes that are required for use in the German calculation. So the system automatically adapts the emission data from the available attributes and automatically adapts reflection losses from barriers and from building facades. And this is the primary difference between Knossos and the German RLS 19 method, that they're different reflection factors and different settings and that you have to take care of. So all of this is now done in LimA. And if you want to support workflows and macros as well, that's also taken care of. For example, whether you use truncation or rounding. So in Germany, for the exposure statistics, you use rounding. In Germany, for the EU reporting, you use truncation. And all of that is supported. Again, that's just an example from Germany to try and make it a little bit easier as to what is possible to be doing. Calculation speed enhancements are done through a range of small improvements, new compiler features, something called GBNZ4, which I'll explain on the next slides. ArtSCE, sound path reuse, which I'll also explain. I'll explain most of these briefly. WGF limit for day and night levels, introducing minimum levels below which you don't have to do the same level of detail. dB failure dynamic error margin. The process in general has been improved, and there are enhancements when you're dealing with facade calculations. And also we deal with more servers. These speed enhancements are important when dealing with larger models, for example, detailed road network and more complex methods. The improvement depends on the model and the use case, and some improvements are focused on calculations at receptor points. So it's not easy for us to give you a percentage change that we can achieve with this. It's an individual thing. I will now run through some of these, the majority of these changes, to give you a little bit more insight into these calculation speed improvements. First one is this thing called GBNZ4. Now, this is a variation on an option that you can set in which optimizes the method of projection. I'll explain this in a bit because it's a little bit complicated, particularly for those who are new to LimA. It's significant for models where the method of projection creates many segments at large source receiver distances. This could be large models and road models, very typically, where there are many potential contributions. And what it does is to limit the barrier segmentation when the barriers are far away from sources and receptors. And thus it optimizes the calculation speed with the ensuring that we still have a good quality. It's a good balance here. The GBNZ option is available already in two configurations, configuration 1 and configuration 2. Configuration 1 and 2 simplified building geometries, and I'll explain that on the next slide. GBNZ1 uses the same minimum distance from source and receiver. And GBNZ2 allows you to set different minimum distances between source and receiver. And GBNZ4 ignores distant objects in the source line segmentation process. Again, I'll explain this a little bit more because it might make it easier to follow. So, as I'm sure you know, if you have a line source and you look at a receiver point, then to do the calculation, you go from the receiver point and draw on perpendicular down to the line source and divide the source into two. You then split that up into other smaller sections until you have sufficient accuracy. Within each segment, you have a virtual point source at each of these locations in the center of the segments. And that's how you do the calculation. When you put a barrier in there, then the segmentation changes. So you have this line now as a segment changing, and maybe you can see that the source points move slightly because the angles change. When I put in GBNZ option, use GBNZ option 1 and 2, then I simplify the building. So if it's a square building or a more complex shape, then I replace it by two linear barriers, when the objects are far away from the source or the receiver, as defined in the configuration. So that's simplifying and that speeds up calculation. But GBNZ4 does something slightly different. So it basically ignores those buildings which are far away from the source or the receiver, and retains the same segmentation as used as if there was no barrier. So we don't have this change in segmentation when this object fulfills the requirements in the configuration. So in general, we have this option we can put in. You have the type of action, you have a minimum distance compared to the diameter of the building, the maximum diameter of the building. You have absolute distances from the source. And if it's separate settings for the receiver, then you have it from the source and the receiver here. You have optional settings to further simplify the configuration at longer distances, and also an option to look at how you deal with an angle of the segmentation as well. However, GBNZ is automatically set with the default values that as listed here when you use the dB failure setting. So in reality, you're automatically doing this when you use dB failure. So if you set dB failure to 1, you actually have a GBNZ setting which ignores the distant buildings. Well, it's only 5, 500, and 500. I'll explain this in the next slide. Number 2 has a slightly a different setting, and number 3 has a smaller setting. And if you just have a GBNZ4 in your LimA 7 calculation file, then you have more rigorous default values. So let's have a look at an example here. And again, remember, here's your barrier-free segmentation. Here's the segmentation when you get a barrier in here. And here's the segmentation back, again, when you can ignore the building. So this is a GBNZ4, which is ignoring the segmentation here. And you've got 5, 200, 100, and a couple of options. 5 means the first value is 5 times the biggest diameter of the building. The 200 and 100 are if the object is more than 200 meters from the receptor. And if you've got a bigger building, then it'll be a longer distance because this number will get bigger. 100 meters from the source if you want to have different settings. If you've got a source at 3 kilometers, then the settings change and how it does the segmentation in a linear interpolation in the same way as we have the segmentation. And you can read that in the handout material and also in the README file. Moving on now to the sound path reuse. This is something that is done when you have octave band subcalculation. So that's for most of the methodology, but not for CR10, which is broadband. And it enables the use of sound path analysis for multiple source receiver combinations under control conditions, which you can decide. And it basically means you can when you have a small angular shift in the receiver position where you have the same view of the same source element and you don't have a large angular change, then you can simplify the source path. You can use the neighboring receiver's source path, speeding up the calculations. This would typically be useful when you're at second or third row receiver points. Be able to do this. I won't run through this today because we're running short of time. I've got some other things I'd like to do, but here on you have both the general setup as well as an example setup. An example setup we've done here includes settings that we propose you start to use initially. We don't have enough experience yet to give you specific recommendations, but this is a good starting point. Other calculation speed enhancements include limiting, looking at results on the WGF results, the facade results for buildings, to those that are greater than a certain level, for example, 60 dB at day and 50 dB at night. And this is useful for hotspot analysis where you're only interested in high noise levels. So you can put that in to speed up calculations. And you can set up these values as you wish. dB failure in itself is quicker in general, but it's also quicker, specifically for facade calculations, as it's if you have a homogeneous situation similar to what you can see on the right here, then we can do some estimation of a noise level at nearby locations where these areas are homogeneous. So this is a prime example of where the dB failure in this one would speed up for the facade calculations. And in addition, we're now able to handle up to 999 different servers in parallel. In the past, to keep track of this, we could only keep track of 99. Now we can handle 999. So for very large models, this is a significant change in calculation speed, because it allows you effectively to use up to 10 times more servers to do your calculation. Probably not interesting for most of us, but for those of you who are doing really large calculations, this is a significant speed enhancement. Another one enhancement I'd like to just briefly talk about is the Barrett Max Source option, and that enables you to find out the most influential sources around a building, and it looks at different noise emitter groups and finds out which ones are the most important, and it can handle up to 5 influential groups for day and night independently. So you can end up with up to 5, a list of the 5 most important emitter groups for the daytime and the 5 most important emitter groups for nighttime around a single residential building. And this is shown in the attributes of the WGF residential building result object after you've done a facade calculation. Let me go on to the next slide to tell you how to set this up and to give you an example of what it looks like. So you need to modify the standard WGF object to include the relevant attributes to show the results. You also have to identify emitter groups in each of the source groups, and all the different source groups are supported. You need to perform a facade calculation and to use this variation in order to in the further options in order to get the results. And it means that for each residential building, the emitter group contributions are calculated, and the worst results for any receiver position around a building object, a residential building objects, are stored in the WGF object. And this leaves up to 5 of these at any point. So if, for example, you had a source that was loud on the daytime on one side of the building, but not at nighttime, then that would pop up in the day, but not in the nighttime. And just quickly to show you an example on this one here, in this one we've looked at the 2 most important sources, and this one here, both for daytime and nighttime, the emitter group U3104 is the most important. You can see that here and here, U3014, and the second most important emitter group for both daytime and night are the R26 group of sources as shown here. You can also see the contribution. So the FR1D relates to the NE1D here. So the U30104 group produces this amount of noise during the daytime, whereas the emitter group 2 produces 57.48. So you can see 60.62 and then 57.48 as the contributions from the 2 main emitter groups during the daytime. But I wanted to progress and show you this one here, because I think this is very useful and interesting for you. This is how to correctly model bridges in Knossos. Now, in the last version we released, the previous version released, we introduced BRGC bridge information attributes for the CRA railway objects. And that meant that you indicated on the railway line when there was a bridge. And then during calculation, a bridge object was virtually added to the model with the correct emission height of 0.5 meters as defined in the Knossos method and the relevant omnidirectional emission data. What is new in the new version of LimA is that bridges and barriers on bridges in Knossos are now handled similarly as to other regulations for road and rail noise. I won't go into details about this one here, but what is important is that if you do have a bridge object in a Knossos rail model, they're fully ignored. It avoids you having duplicate sources. So, and I'll explain why that's interesting and important in a second. So the virtual sources are automatically created, but you don't see the source emission of the virtual source in the CRA object. You just will see that in the calculation results. So what I have here on the left is a railway line and the results from that railway line without a bridge. On the middle here, you can see the results of the railway line when there is a bridge. And you can see, of course, there's much more noise emission when the train is traveling across the bridge. The third picture here is showing that even if I put a bridge object into the model, I don't change the results. So let me just show you what this looks like in LimA in the model itself. So here you can see the a railway model, and in this region here, if I can get close to it, I've got a road going through here and the railway going across on a bridge. So here I go into the attributes. I see my standard railway line has got a BRGC value of 1, which means there's no bridge. But if I go into this section here, then I'll see that I've got a bridge, a constant of 4, which is a very metal bridge defined here. And if I look at the result file, which is this one here, then you can see on the that the result has been adjusted. Going back to this one here, why would you have a bridge object when you have the railway line always already modeled correctly? Well, it's all about consistency, because for the road model, if you're using that in the same area, you want to have the bridge object there. And this means that you don't have to adapt your model to match the railway noise calculation just because the bridge object is there. So the railway model will correctly ignore the impact of the bridge on the noise emission, whereas the same data model can be used for roads without any changes. So that's really quite useful. So as I'm running out of time, I'll close down here just by telling you how to get hold of the latest version and the license files and further information. So to get the latest version and the license files, go to the Software Noise website and log in with your key ID. This will take you to the support page where you can download your license files. And if you go to the bottom of the support page, you can see which of the software you need to download. You'll then follow the installation instructions on this page in order to install the software, and that's how you install it. To learn more in details, in addition to this material that we'll send out, then have a look at the README file, Predictor README file, and the LimA program modifications document that are delivered with the software. So once they're installed, you'll be able to see the files on your hard drive. So I'll now open up for question and answer session. So if you would like to ask questions now, then you are very welcome to do so. If you'd like to wait until after we've finished recording, then we can also do that. So I can see one question here. Alvin, have you read this? Otherwise, I'll have to read it here. Now, regard to railways.
Let me see. It's in the chat. Okay.
Right, yeah, and let me answer this. We've got
Yep. Okay.
this is a question about whether you use Knossos for light rail or trams and things like that. In principle, yes, as long as you have the data for it, yes, you can. Knossos is open for this. The individual member states can decide whether trams are road vehicles or railway vehicles, but in principle, it's typically done with railway noise. Maybe, Erwin, you'd like to comment from the Dutch experience and perspective on this. But basically, yeah, as long as you have the sources in your database, you can deal with the trams in Knossos. Erwin?
Yes, I agree. And Knossos has, in fact, a kind of open structure for the vehicles, for both the cars and the railway material. So, as a user, you can define your own material, both in LimA and in Predictor. And this, of course, needs official data from the government because that would all be based on measurements. There are default settings for the roads in both LimA and Predictor, but I think for the rails, for the railways, there are no default settings. I think you need to really design your own. Is that true,
Yeah.
Douglas? I'm just
From memory,
checking
I
here.
think I saw a report today that I was reviewing a report, and they said they could find 5 standard items in an existing database, but it's very, very limited. I think even if there is anything. So in Predictor and LimA, we have a Spanish database delivered as standard. We have a German database delivered as standard. We have the ability for French database as well, and we're looking at other databases. So say, for example, in Brazil, if you have a specific database done by a measurement campaign, then you can build up that model and put it into Predictor LimA. And if you need help with this, we can do that as well. There's another question as well here, also from Rogerio, regarding wind turbines, and that's looking at low frequencies between 4 and 20 hertz. So this is really looking at amplitude modulation and that really low frequencies. That's outside the scope of the ISO 9613, which doesn't cover this thing. So it's non-audible. ISO 963 deals with audible levels, so it's outside the scope of that. So I'm afraid the answer to that is no, Roger. We'll have to find another solution for that.
Thanks for the question, the response. Okay.
No problems. Good. I see no other questions at the moment, but if anybody would like to raise their hand, and then we can hand over the mic to them and for an additional question. Otherwise, I will conclude, and then we will stop recording, and then you're also free to ask questions after the end of the recording. Okay, so let me do that. So we told you why we think Predictor LimA is great and why you should, if you've not chosen it already, why you should do so. We've told you a little bit about the release of the new version and what it means, and covered some of the major enhancements in both Predictor and LimA. In Predictor, we've got the Knossos Railway enhancements, the new wind turbine functions, the support of the new data formats, EPSG code, the CRTN New Zealand source database, surface database, and also the benefits of calculation speed options. In LimA, you have the support of national interpretations of the Environmental Noise Directive with different statistics, way of looking at statistics. You've got efficient multi-model management, so if you need to deal with national as well as EU reports, you can do that in a smart way. The calculation speed optimization, also details of influential sources around residential buildings, and the smart way of dealing with bridges. We've also told you how to get hold of the latest version in the license files and where to find further information. After you've received the handout material and you have questions, or at any time, you're of course very welcome to ask us any questions you have. If it's a technical question, then please send it to helpdesk@softnoise.com. If it's a commercial question, then please send it to info@softnoise.com, and we will respond as quickly as we can. So thank you very much for attending and for listening to the presentation, and I hope you found it interesting and enjoyable. We will now stop the recording, but Erwin and I will stay online in case you have further questions. Thank you very much. And if you don't want to stay around, you're welcome to say goodbye and leave.